Starting. Good morning, everyone, and welcome back to our last sessions. So it's traditional sessions about highlights from different tracks. And we will start with the highlights from track 1 from Martin Barisic.
All right. Good morning, everyone. Yeah, thanks for the introduction. So this is the summary of track 1, data and metadata organization, management, and access. First, a big thank you to all the speakers we had in this session, the track. So we had 7 sessions, a total of 41 oral presentations, and it was just the 4 track conveners, Diego, Kirby, Mario, and myself. Overall, really very, very interesting content, which was also shown by the many discussions we had. And unfortunately, many of these we had to cut short, but they were then picked up in the coffee breaks. And I have to say that the speakers were very, very disciplined. So we were always on time. Not a single time did we have to signal anyone that they run over time. So I hope I don't run over time now. Just as a quick disclaimer, this is a very personal and biased view, the following slides. So apologies if I don't mention a specific talk. This is by no means a sign of quality. It's just what I personally found most interesting. So there were 7 sessions: storage, networks, clouds and caches, tapes, databases and metadata, data management, and analytics and benchmarks. So quite a wide array of topics. I mean, really each single one of these sessions could perhaps be its own track, which also was shown by the many abstracts we received. So only 41 oral talks, but there was quite a few also posters. I know it's a little bit too late now to encourage you to look at the posters, but they were very good. So look forward to the proceedings. Unfortunately, the posters are not part of this summary, so I really only focused on the oral presentations. First session, storage. As you would expect, there were some overview talks from Bcache, Echo, and EOS. And more specifically this year, there were some kind of common features discussed. For example, erasure coding in XRD, but it was also shown for EOS. Seamlessly accessing remote storage via POSIX. Then there was some exploration of continuity and recovery mechanisms in Ceph, so in case of disaster scenarios. And through all these presentations, some common themes emerged. One of them was that really our storage production deployments are extremely stable and efficient. There's an ongoing performance improvements, both from developers, but also from the site admins who are continuously tuning the storages to give us better performance. Some consolidation of protocols and APIs, and also, as you would imagine, tokens. I mean, this is really everywhere, and the systems are slowly but surely converging now. Maybe one trend as well, object store backends. So this is getting a strong contender for classical file access systems. Networks, there was really one big common theme, and that's that network resources are scarce. So we cannot continue to deal with them as a black box where we pour our data in, it comes out at the other end, and we just ignore that what is happening inside. Because specifically for run 4, the impact to our compute models will be real. So we have to start taking care of this now. So stop thinking of them as a black box. There need to be better ways of monitoring, better ways of throttling and optimizing them. And there were a few projects presented how to address this. So caches, CDNs on one side to reduce the network traffic, then the typical bandwidth reservation and virtual circuits to tune the amount of data transfers, as well as via packet tagging to identify specific network flows and also to be later on able to optimize these. Clouds and caches, it's quite a big move into the direction of cloud storage. So this is becoming more important for quite a few experiments. But at the same time, it's also quite challenging to include these to our classical HAB workflows. So that's just based on the way how we do things. Some projects were proposed how to overcome that. So for example, there's an XRD S3 gateway to really gap this, two worlds, the happy world and the commercial cloud world, and to make this easily usable. Some Russia extensions were presented for Amazon, for Google Cloud Storage and Seal. So this comes out of the box in Russia, but it's also has been shown that this is quite difficult on the operational side. For example, certificate authority chains and conflicts are really painful to overcome, and this is not trivial at all. And then more on the physics workflow side, it was shown how to store and access LHC data through n tuples, and this was both for object stores as well as Amazon S3. On the cache side of things, similar to networks, it is important to understand how we use our systems and to predict resource usage. So this was shown for the source in California petabyte cache, but also then there was a presentation on understanding data access patterns for Dcache. And there it was shown that at one hand, yes, you can predict the popularity of popular data sets, not so well with unpopular ones. And then you can improve the pinning and basically hold these data in cache. Tapes. One, maybe the biggest takeaway message is that the HTTP tape REST API that's becoming quite popular. So the end of SRM is getting closer, hopefully. And there were already the first production deployments being shown. So there's EUCTA, Dcache, HPSSS, and this is working quite well already. There was another presentation which kind of looked into the disk instead of tape usage for archive use cases. And this was a total cost of operation comparison, which was quite interesting because this came to a conclusion you wouldn't really expect, which was that disk is actually cheaper if you have the current hardware estimates, and this is up to half price. CTA was quite a few presentations. So this is a free and open source community tape solution, and they recently evolved this to support also Dcache front ends next to EOS. So this is very nice, and was also shown the CBAC user data backup at CTA. So this is specifically for CERN users, and I'm looking forward to try this out. Atlas Data Carousel working very well. Two new R&D initiatives. For one, data on demand, which is a mechanism where you can reproduce DODs when needed. So they have already been deleted and you reproduce them. And then Smart Archive, which is about how to write data smarter to tape than to decrease recall times. Databases and metadata, which is a quite big topic. So at first it was shown how Rusio can be used as a metadata service for Bell 2. So there was an evaluation being done. And this was very interesting, both because it's the first time this is being done for Rusio, and it was checked how the queries perform, but also how data can be ingested to this metadata store. And it was shown that this Rusio handles this quite well. Then on the conditions database side of things, for Atlas, there's really a major shift coming for Run 4. Big change of the architecture from COOL to CREST. For Alice's condition and calibration database, they showed some quite interesting interval of validity queries. And what I found quite impressive, that this comes in 3 flavors of deployment somewhat. So you can do this locally, in memory, or also grid storage endpoint backed. And then another push more to common interfaces with the HSF conditions database reference implementation, which was shown that this is already 2 implementations for SPhoenix and Dune. Data management for the Nordic Data Lake, they showed how you can incorporate also more geographically distant resources to the federation. And this was done successfully and very, very performant, which was very interesting. Then on a bit of a different type of data management, or at least different than many of our HAB experiments to this, for the HNG photon source. So they have a full stack service in place, also with a quite interesting web interface. And this is, yeah, as I said, quite different than we do things for some other experiments. Then on the LSST side, so to astronomy, Rosie showed this yesterday in her talk in the plenary as well. So they are moving to common HEP tools, Rusio and FTS. One thing which I thought was really interesting is the expansion of raw data. So they will collect around 50 petabytes in a 10-year frame, but their derived data products are a factor 10 bigger, which is kind of rather unique. FTS, 2 talks, very, very interesting. The evolution to real microservices, I find as an FTS user myself, very, very exciting. And then on the Phoenix side, there they showed how to bridge different AI system worlds, how you could, for example, transfer data between an Escape AI-backed data management to a Phoenix one. Okay, and the last session was analytics and benchmarks. Again, a similar theme really emerged here, that monitoring and predictions really key to optimization. So on at BNL for the SDCC facility, they investigated 3 different storage solutions. So there was XRD with Lustre as backend, Dcache and Lustre, and Dcache and ZFS. And spoiler alert, we chose Dcache and ZFS. Then data popularity for cache eviction. Here, again, another cache study. And that was shown that it's really quite difficult to surpass least recently used, so LRU algorithms. It is possible, but then again, it is also quite hard to integrate this kind of technology in our caches. So quite interesting presentation. For the 400 gigabits per second benchmark for XRD, so they had 3 different knobs you can optimize and how to kind of come to these big benchmarks, number of streams, redirector overheads and transfer tool impact. And then for Tune, there was a scaleless being shown for the full data pipeline. And then summary of summary for anyone who, this was too long. Yeah, these are the major points, and I think I'm out of time. So, thanks.
So let's thank again our speaker for the fantastic marketing work. And do you have anybody? Do you have any questions probably to ask Marty? Okay, perfect. That was clear. Thanks a lot again. And now we are moving to online computing, track number 2, and let's welcome Satoru with his presentation about highlights.
Okay, thank you very much for the introduction. So my name is Satoru Yamada, and I'd like to report track 2 highlights on behalf of other track conveners. First of all, I'd like to thank all presenters for track 2. There were 42 talks, 2 plenary talks, and 14 posters. And also, I'd like to thank fellow track conveners, Claire, Ruben, Felice, for organizing the sessions, as well as helping to prepare these summary slides. And unfortunately, I cannot cover all interesting topics presented in the session, but I'll pick up some interesting topics written here. So, as you of course know, demands there are a lot of demands, strong demands for higher throughput in online DQ system in upcoming years. Of course, LHC experiments they started operation in round 3 last year, so we have a lot of reports about 1-year experiment. And also they already started development toward high luminosity LHC, which will start 2029. And also, there are many nuclear experiments ongoing, STAR, Phoenix, and various media management programs, and also future electron-ion collider. And there are neutron experiment. Proto-DUNE and the DUNE detector will be in operation in around 2030. And also, as for E plus C minus collider, Well2 experiment, data size is increasing as it is on the way to the designed luminosity. Okay, so the first topic is trigger. That is a very important part of online DAQ. And there are two very important, but basically conflicting demands for trigger. One is we'd like to decrease throughput to backend DAQ. But on the other hand, we need to keep trigger efficiency high. So in this conference, I noticed there are two trends. One is moving hardware trigger to software PC farm. That is a triggerless or continuous readout. And also the opposite direction. So I mean, high-level trigger, hardware trigger becomes more smart, and it is more like a high-level trigger by software so far. Okay, let me explain. And as for the triggerless and the streaming readout, I'm going to hear the LSCB and ALICE successfully operated the new DAQ system. As for LSCB, triggerless DAQ was in operational in round 3, and they'd like to increase trigger efficiency by using a more sophisticated software trigger instead of hardware trigger. And it has been successful for the first part of round 3. And also another development is ongoing to use more intelligent trigger in their system, because flexibility is a key point for this triggerless DAQ system. And also as for ALICE, they also developed a new DAQ system or to FLP for round 3, and they continuously reading out TBC data by readout board, and it is excellent initial performance and quite promising for us. And as for the towards the high density LSC, CMS and Atlas people are developing smarter level 1 trigger, because pile-up situation in HLSC will be very harsh. So as for CMS, the particle flow scheme currently used for offline reconstruction will be brought to a level 1 hardware trigger, and they will include tracking trigger and other special triggers or in level 1 trigger, and also Atlas for high-density LSC. Really, HLT-like object level and event level reconstruction will be performed inside hardware trigger. So next topic is accelerated computing. So this is widely used in online computing to accelerate computing by GPU or FPGA. And already in round 3, ALICE uses a GPU for online and offline reconstruction. And without this GPU, more than 2,000 servers will be needed. And also CMS round 3, 40% reduction has been achieved by using GPU for acceleration. So there's a very good result. And as for also FPGA can be used for accelerated computing. In Atlas, graph neural network will be implemented in FPGA and event filter for high mystery LHC. And FPGA resource constraints is an issue. So they are trying to reduce the resource usage by introducing quantization or pruning. And also, there's an interesting report about the triggerless DAQ for anomaly detection. So they are preparing some test bench using drift tube. And FPGA is used for reconstruction by making use of neural network. And also, it sounds interesting. This kind of small, simple triggerless DAQ system can be attached to main large DAQ for some special study. And the next topic is a common readout device. So readout device is in online DAQ is the interface between front-end electronics and off-the-shelf world, which consists of servers and switches. And actually, structure is somewhat similar for different experiments. It is equipped with large FPGA and with many transceivers. And then, so currently there are two types of board used for many experiments, FedEx and PCI-40. And it has been used by multiple different experiments. I think it works fine. As for network and event building, so data flow becomes larger, and kind of good strategies, of course, to take advantage of the growing bandwidth capability of network devices. But however, simply bringing off-the-shelf products may not work for extreme use cases in HEP experiments. So this is a figure is a simulation result for the minimum buffer required for network switch for the high luminosity LHC Atlas case. And the monitoring and the control system becoming smart. So this is a very impressive picture, and the machine learning and AI used for detecting error in DQM plots instead by looking by human eye. And the right figure shows DQM plots in Blue X experiment at JLab, and AI can certainly detect some error in those DQM plots. And also, it is used some automated configurations such as a high voltage control to get a stable gain. Okay, and as for the quality monitor, there is an attempt in Alice to combine online and offline quality assurance and monitoring in Run 3. So they are collecting, this system collecting monitoring data both from online pattern as well as a grid system, and make a good check of data. And of course, the data flow becomes increasing for this project. So we are using very much many resources to handle this monitoring data. And another topic is management tools. So containerized DAQ on Kubernetes was reported by Dune and CMS colleagues. And of course, there are a lot of hundreds of PC servers to distribute the DAQ application. So it will be very useful to use this kind of management tools. And it can remove dependency on OS and library as well. And currently study is ongoing for the two experiments. And one question is to what extent can this Kubernetes control the DAQ system? Okay, so this is the last slide. So let me thank again for all your contributions and discussions, and hopefully we can successfully ride the tide of data in coming years. Thank you very much.
Many thanks for this nice overview. And anybody, do you have any questions maybe to track to conveners? Okay, that's an easy. So thanks a lot again. So now we're moving to offline computing, and I would like to introduce Marilena Bandiera-Monte, who will tell us about highlights of her track.
Is this already the screen? Doesn't work. Thanks. Okay, I will be presenting the highlights for the track 3, which is about offline computing. First of all, some numbers. So as the name clearly says, this track is covering all of the offline computing steps. We had thematic sessions on simulation, on reconstruction, data preparation, and physics performance. We had quite a number of abstracts, 94 in total, and we organized 7 sessions with 41 orals, and also 2 crossover sessions together with track 9. And the topic was fast simulation with machine learning, and I will be partially covering this topic in this talk. If you didn't attend much of the track 3 offline computing, you might wonder how it was. So you might wonder if it was fun. And maybe you can try to ask the question to ChatGPT and see if it can answer your question. And unfortunately, it seems as an artificial intelligence language model, it cannot really answer your question, doesn't have feelings, it's not allowed to understand if it was fun or not. But me, as a human being, I can actually tell it was really fun. So thank you to all of the speakers, thank you to all of you for participating in this session. We had really nice participation, both from the point of view of numbers of people participating to our track, but also the atmosphere was quite nice. We had really excellent talks, constructive discussions, and speakers were very nice, always in time. And we really had a lot of questions also to follow up offline. So this was really, really nice. So now let me talk about what is guiding basically the computing challenges which are guiding the R&D in the offline computing right now. Of course, for what concerns the LHC experiments, high energy physics in general, we are pointing to high luminosity LHC. So you might be familiar with these 2 plots here from CMS and Atlas, which basically are showing that we really need to put a lot of effort in aggressive R&Ds if we really want to meet our goals for the iLumi challenges. So the main focus in offline computing is to try to speed up the part of the chain which are the most time consuming. And for sure, one part is the simulation, but this has been true for the past couple of years. It was true already for run 3, and now it's also reconstruction coming in the picture, because you probably know that with the high pileup that we expect to have for iLumi, the reconstruction doesn't really scale nicely with the pileup. And for example, CMS is projecting that reconstruction will take 2/3 of their total CPU time. So this is really something important that needs to be addressed. So we have tried to highlight few trends in offline computing. One for sure is machine learning. Machine learning is really pervasive, so it's now basically it already entered most of the traditional aspects for high energy physics offline computing. So we had talks, many contributions about fast and also ultra fast simulation approaches. Some talks trying to resolve the ambiguity, improve the ambiguity resolution in reconstruction using machine learning. Also, machine learning is entering the data quality monitoring, and it's very much used in tracking with graph neural network, for example, in the Extra-Track project. Another line is for sure trying to exploit GPUs, and the R&D in this topic is really gaining traction, even for the most complex workflows. So, for example, Monte Carlo simulation, we have two new projects which are really gaining traction and starting to present very nice results, Adept and Accelerators. We have some contributions in trying to port, track, and primary vertex reconstruction on GPUs, for example, with the TrackCC project. And also we have seen lots of effort. We had many talks from Gen 4 showing this effort to improve Gen 4 in multi-directions. So trying to meet the needs of the experiment. So addressing the CPU speed up, for example, with new library and the new optimizations, but also targeting the improvement of the physics accuracy with the introduction of new models and improving the analysis tools. Also, we had a few nice talks about event generation. There is this effort trying to modernize the event generation, which is also another very important part of the offline computing, which is also taking a lot of CPU time. And the effort there is also to speed up the event generation. One thing which I really find nice and interesting is that it's clear that there is an increased synergy between experiments. I think this is one of the main positive outcomes of our international collaborations, and we see that there is this increased also enthusiasm in adopting common solutions. For example, ACTS, Gaudi framework, DD4App, and we had some very nice feedback and talks from new experiments which are presenting the status of their offline software development. And it's clear that they are learning from the past experience of the other experiments. So this is really nice from the point of view of the collaboration between different experiments. So we have presented the EPIC collaboration, the Juno and Dune status of their offline software. So about machine learning solutions for fast simulation, as I said, we had to have two dedicated tracks to this topic. And mainly, all of the different efforts are addressing the simulation of highly granular calorimeters. What is interesting is that new approaches are being tried in this respect. For example, one over the others that took my attention is the application of diffusion models using point clouds to solve to address the simulation in hadronic, but also electromagnetic calorimeters. There are also first attempts at applying foundation models to simulation, many talks on normalizing flow and deep generative models. What I want to say here also highlight is that machine learning is not just in the R&D phase, but actually it's getting also into production. In fact, for example, in Atlas, there is already a fast simulation model using GANs, which is in production for Run 2, and it's going to be deployed also for Run 3. Another interesting contribution came from the LHB experiment with their ultra-fast simulation Lamar, which is basically a strategy which is not only trying to skip the simulation step, but also skip in one go also the reconstruction. So with this ultra-fast simulation, basically they substitute the two steps with a set of pipelines which are machine learning based. And these are modular parameterizations, basically, that replace the two steps. And they show very nice results on performances of their tracking system model, the way they are able to discriminate particles and also reproduce the equal simulation. About simulation on GPUs, we had a talk by the Adept project. This is a project to simulate EM showers particle transport on GPUs. Basically, if you want to do that, you have two main interlocutors. the physics and the geometry. And of course, if you want to run on GPUs, you have to be able to run those components on GPUs. For what concerns the physics, we have now a new library, which is called G4HappyM, which is meant to be run on GPUs. It's a compact library specifically designed for high energy physics, and it can be run already on GPUs. For the geometry part, the work is based on VecGeom, which is a vectorized geometry library that initially already supported the CUDA GPUs with CUDA, and now there is this very interesting effort in evolving the GPU support with a new geometry modeling. It's a bounded surface modeling which scales much better on GPUs with respect to what the classical way of representing geometry, which is a hierarchical way, does normally. So they have showed very nice results, and actually the status is that it's possible to run a full EM shower development on GPUs, profiting both from CPU and GPU. So you run a Gen4 simulation and you offload the electromagnetic part on GPUs. So this is really nice progress. About physics performance, we had talks mainly focusing on trying to improve the quality of the physics objects. So for example, Bell2 has shown that their calibrations are basically ready for high precision physics. We had some talks, as I was mentioning before, about applying machine learning to CMS data quality monitoring. And the EPIC collaboration showed and talked about the performances and design of their offline software. About reconstruction, a key player in reconstruction right now is for sure ACTS. ACTS stands for a common tracking software, and the goal of this project is to, as the name says, to provide the common solutions for tracking for all of the experiments. So it's really a cross-experiment project, and we had a lot of contributions, both from the internal point of view, so from developers of ACTS, but also from experiments which are adopting ACTS successfully. So for example, we had TrackCC project was presented, and it was nice to see that actually it's possible to do track reconstruction on GPUs, and GPUs are becoming competitive with IPyLab, which is really what we wanted to hear. And another contribution is about improving the event data model of ACTS towards it being more flexible and also experiment agnostic. These are some nice results that were presented by SuperTau Sharm facility about the performances of their track reconstruction using ACTS. And also a very interesting talk about improving the ambiguity resolver by using machine learning techniques, as I was mentioning, basically applying clustering plus ranking neural network on top of the combinatorial Kalman filter. On data preparation, basically the main need is to be able to handle large data volume already in the current experiments, but mostly this will be true for future HAP experiments. So really what you need there is to have efficient data processing, transfer, and storage. And we had few talks from Atlas and also Dune showing, for example, performances of data compression and also the way the data are distributed over the grid. You also need flexible and capable offline frameworks. Very nice talk from the Juno collaboration about Sniper, their offline computing infrastructure. And one important aspect is also related to the improving the visualization. We had a nice talk from CMS about their routine-based visualization. Let me conclude with thanking really all of the speakers, all of you for participating to this conference. And I wanted just to leave a final message, which I think it's very much important in this peculiar time we are living. Thanks very much.
Thank you so much, Marilena. So I don't know, like anybody, do you have any questions? Maybe just something to clarify. Okay, it was clear. Thanks a lot. And Now we're inviting track convener from track 4, distributed computing, Katie. Oops. No. Yeah, that's right.
Hi there. I'm Katie Ellis, and I'm presenting on behalf of the Track 4 conveners, Rohini, Fernando, Hideki, and myself. And I have to say it was a pleasure to work with them, and thanks for all their efforts. This is the distributed computing track, quite a general title, so we have quite a range of topics. Here are the themes of Track 4. I'm not going to go through the list now because I'm going to have a slide on each one, but if you want to look for any of your favorite talks or anything I say you're interested in, then please go to the link to the contributions there and find those talks. So we had a very good atmosphere in the room, a full complement of 42 talks, which we narrowed down from over 100 abstracts, which was a tricky process, but at least many of those got to move to different tracks. So the first session was on analysis workflows, modeling and optimization. And we had a few talks on Atlas use case for quite complex workflows. For example, using Panda to map distributed machine learning to our heterogeneous resources, the grid, HPC, and cloud GPUs. We also had an overview of the digital twin infrastructure and how it will enable multiple use cases in different fields. There was the analysis grand challenge, benchmarking results using CMS open data. The second session was on quite high-level computing strategies and the evolution of those. So there was the big science computing models for both old and new experiments, Atlas, CMS, Einstein Telescope, Juno, and the LIGO Virgo PACRA collaboration all gave talks. It's clear that many experiments are getting ready for the next decade of data taking in neutrino physics, gravitational waves, and high energy physics. And there were established data and workload frameworks being prepared for upcoming challenges. So we know what those are: the larger data sets requiring more efficient storage, heterogeneous architectures, modernizing of software, making the use of varied computing resources across the grid, HPCs, and cloud. And of course, the recurring topic of this conference, environmental awareness and how we can increase our efficiency while also lowering our carbon footprint. On Tuesday, we had a session on infrastructure and services, and there were a couple of talks on how to best support multiple experiments across multiple sites in an easy to handle way. And there was big support for central orchestration of services, for example, using tools like Kubernetes. We had a talk from CVMFS, who noted that as every part of our system increases in size, then CVMFS also has to keep up and maintain performance. And we had a talk about the auditor software, which is the accounting of opportunistic resources. As opportunistic resources are more and more common, these really need to be properly accounted for. And Michael Voller showed a nice diagram there on the right, showing data being collected from a number of sources and then farmed out to appropriate places. The next session was on monitoring, testing, and analytics. We had significant updates from both Atlas and CMS on their monitoring systems, and also an overview of new Alice monitoring called Site Sonar. There was another interesting talk on the monitoring of multi-core Alice jobs, which spawn parallel processes. The chart on the right there is a Gantt chart showing these processes being monitored live through the lifetime of the job and the number of processes that are being spawned, and also how those spawned jobs need to be accounted for. There was a very interesting talk on data popularity forecasting and job queue optimization in Atlas, and showing how new metrics can improve the utilization, for example, by smoothing out the balance of different types of jobs waiting in the queue. And the plot on the left there shows an efficient type system on the left versus an inefficient type system on the right, where queues are being either over or underutilized. The last session on Tuesday was security and tokens. We had a talk on Security Operations Center, which is a new initiative, and also a suggestion of how to start, sites could start monitoring their security better via this PDNS SOC. And they have a lovely emblem there on the right, and I understand that merchandise is available. So this is to emphasize the collaborative and international nature of how we should get together with security improvements or to better monitor our sites. So sites were being invited to come together and protect the infrastructure as a group. Then there was a talk on multi-factor authentication at CERN. And the chart on the bottom right there shows the migration of users at CERN being moved to this multi-factor authentication. Of course, there were also plans and status from various WLTG experiments on the move to tokens. And of course, we all need to plan this very carefully. The token migration should not be considered a drop-in replacement. There's clearly a lot of work that goes into this change. On yesterday, we then had a session on distributed storage and computing resources. So it's clear that several distributed computing technologies are allowing the combination of geographically distant sites as one big virtual lab. So a user would not even see the differences, they just submit to one big cluster. And these are showing comparable performance as a single site, although we did review some work by Justas on local versus remote reads, which of course need to be not only studied, but also continually monitored if we're going to be having these geographically distant sites. And one convener wanted to point out that the diverse nature of our personnel reflects the sort of diverse nature of our computing resources, and we should embrace heterogeneity by integrating GPU and our non-x86 CPU with our mainline grid computing. Well, the final session was on workload management, and there were several reports of reuse of workload management systems by new experiments, which was very good to hear. For example, the Vera Rubin Observatory reported good progress with their testing at scale with Panda, and the CTAO saw improvements with their Dirac workload management, and they were also introducing support for this common workflow language. There were improvements reported to existing workload management systems as well, such as the Lasso cluster extension to include remote resources. And there was additional automation with intelligent dynamic scheduling of opportunistic resources with the new Alice workload management Jalian. In the plot on the bottom right there was an interesting study of how Alice could use spare resources, spare cores that were underutilized, and this was going to increase their efficiency in a very nice way. And that's the end of my talk. Thank you very much.
Thanks a lot for such amazing overview. And just in case, if anybody wants to maybe add, comment, or...
Let me ask one question as a good session chair at the back. Okay. So you mentioned CVMFS, and it kind of reminds me of AFS, which was going to be around forever until it suddenly wasn't. Did you spot any possible pressure points or pain points where there might be early warning signs of something that we need to pay attention to in the coming years in terms of common infrastructure, maybe like CVMFS?
Oh, that's a tough one. Nothing comes to mind. Does any of the other conveners want to chip in? I don't see any of them around.
Don't really know where I'm speaking to. There you are. Okay. Well, as we see with the workload management systems as well, if there's reuse and if there's buy-in from more communities, that helps. And socializing more of these technologies and more of the tools that are part of the stack inherently to other communities will probably help the lifetime of.
I think it was clear from some of the newer experiments taking on some of the older experiments software that they were aware of the work they would have to do themselves in order to take somebody else's bespoke solution and convert it into their own bespoke solution. So I think that was clear that they were aware of that.
Thanks. There we go. I've provoked a question.
Well, just thinking about your question, I was wondering now that the only big thing that I could think of where our software very much relies on somebody else is with the Linux distributions right now. That one worried me a bit when we were going through the whole exercise of choosing the next Linux distribution for the LHC experiments. I don't know, with file systems, well, by now we are developing our own stuff because, yeah, AFS was a similar issue that it was developed by somebody else. So, yeah, I'm worried about Linux distributions right now.
So do we need to in-house that, Attila?
We did that before.
Okay, so I think since there is no any more questions, let's think again of a fantastic team. Where I want to introduce Elizabeth Sexton-Kennedy with an overview of track 5 collaborative computing.
All right, so I'm here to talk about sustainable and collaborative software engineering. I've always liked the software engineering topics. It focuses on our processes and our tools to improve how we make software and computing systems. I'm not going to read these topics because I'm going to go through each one. But I will say that the real theme of this, and you can see it from the topic names, is sustaining through sharing of common tools, which is something we were just talking about. So we had two talks, nice talks about Julia as maybe being a sweet spot between C++ performance and Python ergonomics. Including one concrete example with two different implementations of FastJet. And, you know, the plot here shows ease of access to hard coding
and then performance-wise, slow to fast. And Julia is over here, where C++ is over here. And Python is easy, but it's slow. So that's one tool, but interoperability between different languages and different hardware platforms was also a key topic of this session. Also in this session, we had 2 talks about engaging and training the community. You heard in a plenary session from Marcus about the user-centered design. We heard more details, including results of the surveys and how they're trying to engage their community. And we had heard from Subir about the IRIS-HEP initiatives to improve both the available materials for training. They're generating a wealth of materials in addition to organizing the training events. And he really points out that we have a responsibility to democratize our science, because different people in different regions and going to with different backgrounds can have more or less exposure to education in their institutions. And if we really want to get ideas about our physics from everywhere, all over the world, then we really need to pay more attention to the training aspects of what we do. So next session was on CI and build infrastructure. So it was a common trend across the experiments to use orchestration and containers, Kubernetes clusters, and Alice is moving to use Nomad. And here's an architectural overview. It's from HashiCorp, and they integrate together Nomad, Vault, and Console. Vault is a secrets management system. Then, even in the area of web deployment and development, the CERN Web Service Group has moved to automate more configuration and delegating some of this specialization of web pages to users. Glance we had 5 contributions from Glance throughout this conference, many of them in our track. It's used, I was surprised to learn it was used by 3 different LHC experiments. So CMS, the one I'm on, is the odd man out. With, it has 12 active developers supporting 20 plus web systems. I would say that their model of sustainability is through their program of collaboration with the Computer Science Institute in South America that brings in new people and sustains all of these tools for the past 20 years. And the sharing of the infrastructure across the experiments allows it to be improved. We heard about synchronization improvements, search, and infrastructure improvements. Sustainable analysis. So we heard about COFIA, which I believe it was talked about in many other sessions as well, and it uses this open source Pythonic ecosystem. What was concentrated on for our session was this new tool called Dask Awkward, and that fundamentally changes how we can describe an analysis. So it is a declarative analysis based paradigm, and it uses Dask task graphs, and they get rendered into an optimized and general complete declarative analysis description language. This work represents the culmination of 4 years of R&D. We also heard about Luigi analysis workflow in Python. It's a large-scale end-to-end analysis, automation, and distributed resources designed to fully decouple the three aspects: run location, the software environment, and the storage location. So also in sustainable analysis, we heard analysis of physics analysis. So the idea is to learn from the Git repositories, and since CMS has its full history public, they analyze the CMS repositories. And what I thought was interesting is that they learn useful things for evolving and maintaining the software. So they can learn that which versions are being adopted over time, and you can see this trend from the old version slowly going away and being taken up by the new version. They can find out the most common function calls and patterns and decide if and when a feature can be deprecated. Something that they say, oh, nobody must, this can't be such an important function. And they find through these analytics that many people are using and they can't toss it away. So they also discover which libraries are being used together, and that helps motivate integrating those libraries together more tightly to help the users. Then there's these LHCB's Monte Carlo submit infrastructure is a new tool for them. And what it does is it tries to improve the quality of the simulations that are being scaled up to go onto the grid by integrating in the data quality, the simulation data quality in with the tool itself. So you make a YAML-based description like this one over here, and gets reviewed, CI tested, and then only then, after it passes those tests, does it go into the full simulation system. So we heard about Monte Carlo infrastructure and simulations. So a new generator for hadronic physics meant to handle everything from PP collisions all the way to heavy ion collisions. Since it's new and it needs to be tuned, one of the first things they did was integrate Rivet. Rivet is a system for testing and feeding data models into software in a sense. And they find that this integration has been really effective for testing and finding the best parameters for the generator itself. Then we heard from GEMC, and the question they ask is, can we define a GEANT4 simulation that is entirely driven from a database description? And there was a little bit of debate about that in the session, but the proponents believe that they've had some real successes here. And yeah, the long-term goal was, okay, yes, that's the databases. So then we had to talk about LCIO turning 20. And, the long-term goal was to encourage interoperability of worldwide linear collider simulation, reconstruction, analysis programs. And since it is so old, it's a bit legacy, a lot of legacy software. But what they did was they built a vibrant community through this shared software. And because of that, they can move to Key for HEP and EDM for HEP, along with the other experiments, and really take advantage of this for a large group of people. We also heard about Darshan, which is a lightweight IO containerization tool that captures concise views and entire traces of applications IO behavior. We heard about a refactoring of Gauss into Gauss on Gaussino. It's so Gauss is the full simulation framework, but they extracted out a core of experiment independent components into this Gauss. And it can be, so Gaussino itself can be used as a standalone simulation, and it's an ideal test bed for early detector studies. Sustainable frameworks. So Key4HEP is a turnkey system providing components and building blocks for many efforts in the future collider world. You heard me say that LCIO world is moving to it. So that was interesting to hear about. And we also heard about MELD. It's exploring the feasibility of a framework-less framework for Dune. And it's an analysis of functional programming approaches to frameworks. And finally, the Open Data Detector Project is trying to establish the next generation detector modeling tools for algorithmic and computing R&D. This open software is built on other pieces of open software, and it attempts to be the next step in generating these, like the tracking and the Callow challenges, the code to be investigated and optimized. And it's all built inside this Key4HEP ecosystem. And then finally, we heard about the pain of open sourcing and publication of the Bell 2 software stack. It is, I remember when CMS did this, and it takes a lot of cleanup of the code to be able to do that. You know, you can get, when something's private inside, you can get away with doing things that are not 100% kosher, but when you make it public, you got to remove all of that. And so it's a lot of work, but they claim that it was well worth it. They had no negative consequences so far, and now they can cite their software, they can get Google Summer of Code because it's open source, and you know, it helps their community with job applications because they can point to something and say, this is what I did. So that's it for me. A big thank you to the CHEP organizers and all the participants for making this CHEP truly enjoyable experience. It's great to be back together again.
So I have a session chair question for you, Liz, before Attila goes to the microphone again. Summarizing lessons learned from HEP for other communities and thinking ahead, what's the main challenge for software sustainability?
So I think it's like we were saying for the Linux distributions, you have to have a community, a large group of people who are committing to keeping it going because, you know, we are all built upon other things, right? There's a whole stack of things. And sometimes the things underneath us are not under our control. And it breaks things up further up in the stack. But if you have a whole community developed, you know, around, dependent on that upper thing, they'll fix it, you know. They'll migrate the tool to, you know, the next version of the underlying tool. And so it needs constant, every piece of software needs constant maintenance in terms of CI/CD because we have such huge complex software stacks, you know, Atlas 5 million, CMS is the same number of lines of code and things like that.
And how do you build that community consensus then? I guess that's the challenge, right?
Conferences like this really help a lot, I think. But I think also people need to see value in adopting somebody else's tool and, you know, understand that man years of FTE effort have gone into developing some of these. And I remember once talking to Vincenzo about frameworks and, is it possible to have an experiment independent framework? And, it's more, you might look at a particular technology and say, oh, I can't use that. But it's more the community and evolving it towards everybody's needs that is more important than actually where you start from.
So Liz,
Yeah.
I have first a question and possibly a long comment afterwards.
Okay.
So the question is, how was the attendance in track 5 throughout the week?
So we had a smaller room, but it was, I don't know, 30 or more people each time.
Oh, really? Okay. Because I was not super happy with the organization of this track. I felt that well, it just overlapped with practically all the other tracks, and I just by mistake found some of the talks that were in this track, and I heard other people saying that they had no idea that that talks that were related to their thing, simulation or offline software or whatnot, ended up in this track.
Yeah.
So
I gotta say that there was, like other speakers have said, their tracks were overwhelmed with abstracts. We were not, right? And so when it was a high quality abstract, but wouldn't fit into, say, offline, if it could be in any way, passed as a tool for a tool. So, you saw Jump 4 as a toolkit, right? But there are all these other tools developed around that toolkit, things for geometry and all kinds of tools for tools. And if it had any flavor like that, it was injected into Archive. That's all that happened.
Let me make a comment from the sort of track organization point of view. I mean, I think software sustainability doesn't get the attention that it deserves, so it was really important to have a separate track. Now, parallels being parallels, that does mean that you're going to have a lot of overlap. But
right, but I guess, well, from my perspective, it's sort of vaguely defined what software sustainability is. Then somebody shows, well, hey, here's a new piece of software that I'm developing, whether that's software sustainability or it's offline software or what.
So maybe we need to have the discussion to work out the problem.
Yeah.
Maybe I can comment on that. There's also a track convenient. Actually, coming back to what Paul said about what is software sustainability, and I would, in one word, itself, meaning the sustainability itself. And what I mean by that is very often we are driven by the needs when we develop software, but unfortunately, we don't plan longer term. We attack some solution, and that's it. There's no longer term vision. One of the issues probably is actually from a management point of view, meaning in the experiments, again, we saw go with solutions, but if you think about, how's this going to happen, evolving on the next decade scale, which is a good time scale anyway for an LG experiment, you will probably get the answer, I have no idea. So this is actually the problem. In that sense, I think track 5 does have a place and a meaning, because it is really a problem that we have, and it's a cultural problem, and it's there since ever, and yeah, very complicated to solve.
So we're having a discussion. Another comment?
Yes, again, as track convener, just very quickly, as track convener and a non-native English speaker, I think the name was off. It should have been called, in my opinion, software frameworks and tools, and then it would have been clear what was inside. Software sustainability might be an interesting concept, but I think it puts people off, especially for submitting the talks. There were many talks that went in offline simply because I think people didn't know what software sustainability was. Just my 2 cents as minority.
We have questions. We have time for.
I just have a brief comment. I would like to compliment Liz on very carefully explaining what everything was in her talk. Just a comment in general is that people are doing wonderful things, and people from outside your community cannot always understand what that software package you just referred to was. So I think it might be useful to come up with a glossary that explains at least the codes that you use in your field, preferably name, description, link to the documentation, and include it in all of your talks so that somebody reading it after the fact isn't sitting there not listening to you and Googling, what the hell are they talking about? Okay, thank you.
Thanks a lot.
Name, description, link to the documentation, and include it in all of your talks so that somebody reading it after the fact isn't sitting there not listening to you and Googling, what the hell are they talking about? Okay, thank you.
Thanks a lot. Let's thank again Lies for a fantastic overview. And now we're moving to track 6, physics tools, and welcome, Stefan. Please go ahead and show us.
Well, thank you. When you say physics analysis tools, it's not really always clear to everybody what this means, because physics analysis is basically anything you do from when the detector takes the data until you get your final result. What we try to do in this track is to take all the parts after your experiment provided to you some highly or not so highly derived data format. So the reconstruction, the Monte Carlo simulation, the heavy lifting, so to say, that happens on the grid traditionally in LHC experiments, that's already done. And you have a more or less derived data format, and you're trying to analyze this data format and getting the final results out of this. So we had in total 6 tracks, and we tried to give them some more or less meaningful titles, but you see we didn't always succeed. For statistical inference and fitting, I was quite happy. We were quite okay with this. So first of all, we had 3 talks on RoofFit. I find this quite impressive, also close to my heart, because I used to be a RoofFit developer, but I haven't touched it since more than 2 years. But they are still going strong. They're doing amazing things. They have CUDA support. They do automatic differentiation, which if you know how RoofFit works and how C++ works, it's not trivial. And nevertheless, they're managing and they're seeing speedups. And also they are doing multiprocessing to speed up the Higgs fits. This is basically how we discovered the Higgs. So I'm very happy to see that they're still going strong. We had a talk on Minui, the 50-year-old minimizer, the workhorse in high energy physics. And it's still going strong. It's outperforming still to this day many minimizers for the kind of workflows that we are doing. I find this pretty amazing. And if you want to know what's coming up in Minui 2, that's your talk. We had talks on Bayesian methodologies. You know, we're pretty frequentists at the LHC, but they are showing how to get the base into his factory things. And also a multi-dimensional event-by-event weighting procedure to separate signal and background. So that was a pretty consistent session, great talks, great questions. Then on the second session, we went to I/O and data formats. And we had 2 talks on HDF5. So June wants to use HDF5 to dump the raw detector data into a file. And we had also somebody, Tom, who showed us how to have a T3-like thing and put it into HDF5. If you're wondering why you would do this, you have to look at the talk. So then Root entered the stage, and they showed us where we're going to go in terms of I/O in the coming years. So they showed the path to production for our N-tuple, the successor of T3. And if you look at this, I find what I see pretty important with view to the Halumi LHC, because you know that we're not only limited in computing, but we're also limited in storage. But with our N-tuple, by just taking the same data and dumping them in our N-tuple, you're saving up to, I don't know exactly, 20% of the space, just like this, by evolving the file format. And also, you see here why you want to use this in the future, because depending on what you read and where you read from, you can get speedups of a factor 3 in comparison to what they call always industry standard, Apache Parquet, or even more if you compare with HDF5. And the reason is that in high energy physics, and I think in nuclear physics too, but I'm not so sure about this, we have this weird data format where the size of every record changes with every event. We have more or less jets, we have more or less electrons. And if you are analyzing something like this, you need a specific file format for this. And well, that's what we have in Root. We also saw how it's being integrated in Athena. And then we had an interesting talk. If you are into hammering with 256 threads on an IO subsystem. So if you are into the nitty-gritty details of what happens when you hammer with 200 threads on an atomic, this talk is your talk. You have to look at this. And if you want to know what's going on with our data frame in the future, how it could evolve, then you should look into the boosting our data frame performance with byte processing, because there is a line of development that might speed up the analysis workflow in a data frame even more. Okay, so that was two pretty consistent tracks. The next one we had was machine learning. And now you might ask, why do we have machine learning in the analysis tools and not in the machine learning track? And the reason is relatively simple. We had a lot of machine learning abstracts being submitted, and ours were pretty good. So the machine learning people pushed everything that remotely looked like also it's doing analysis into our track, and we were happy to take it. So we had to talk about building high dimensional data using clustering algorithms. And we had somebody who was explaining us how to speed up the matrix element methods using deep learning. You know, if you have done it at least once, that matrix elements are extremely slow. So it's nice to have deep learning help you out. We had two talks on deep generative models. If often you have to simulate the background, but maybe your Monte Carlo generator doesn't really simulate well, you have to resort to data-driven backgrounds. Or, and this is the alternative, what you can do, you can use your data to train a neural net, and then your neural net is generating a background distribution for you. The second one is here. They're pretty similar, both pretty interesting talks. We also have people who are approximating likelihood distributions using machine learning, because often likelihood distributions are not really easy to simulate or to compute. And they used machine learning to approximate the distributions, and then they did statistical tests on those approximated distributions. That's quite impressive. And a similar thing is going on here, where they also used machine learning to uphold the likelihoods, which are otherwise intractable. So far, we were pretty happy with our sessions, but then you see that everything that has to do with physics analysis is not always very consistent. It doesn't always go in one bucket. And we had here a session on reconstruction and amplitude fitting. You would see that it didn't do too well. The first one was a perfect fit, kinematic time filter approach. So it's a toolkit for low momentum track fitting with high precision. And then we had Lauren, I don't know how to pronounce, because I didn't physically attend the session because I was giving my own talk. It's in the Java-based IO implementation for food. Why we didn't push it into the IO? Well, we just didn't have a slot, so I'm really sorry, Andrew, that you had to go here, but thanks for the talk anyway. Then we came back to amplitude, no, not really, the four-body decays. Pretty interesting, because for the four-body decays, computationally expensive. So OpenMP, CUDA accelerations, TPB threads, all in this framework, if you want to see it. Then we had somebody who wanted to show us what happens when you include Monte Carlo uncertainties into generator tuning. Whether or not they succeeded, that's for you to find out by looking at this talk. And then something which is really nice to see for an LHC person like me, because this is really what chat is about. You see the other half of the community in the chat. You know, how did Wouter say it? I'm for the silent M in chat. So we had a talk on how they're going to do the software at the Electron Ion Collider and how they unify the existing software frameworks. Okay, thank you. And then we went on to physics analysis workflows. Pretty interesting session. This is all about how do you schedule your analysis on a larger cluster. For example, on tier 1, Daniela Stiga showed us what happens when you use our data frame to replace and to rewrite, so to say, an old analysis, and they store a factor 8 speed up. Alexander Held with the Analysis Grand Challenge is a toolkit. You could say it's a collection of realistic workflows for people to benchmark what they're doing. Is extremely interesting for the software development. If you want to develop something which is really close to reality and you want to benchmark how well you're doing. And this is exactly what Vincenzo did. So he used the Analysis Grand Challenge to show off what a data frame is doing, and it's great multi-threading execution that this code does work. More physics analysis workflow. We had partial wave analysis, highly multi-threaded. We had analysis productions per spur, where LSCB produces their M tuples for analysis, fully integrated in web pages with live histogram viewing. And we had Root Interactive. It's an expert tool for Alice detector experts to really understand what's going on with the detector. And then we had a funny session, because this is everything where we couldn't really put our finger on it. And we didn't have a name up to yesterday. So if you look at Indico, the sessions will have a name. And when I made the slides with my colleagues, suddenly it was called new tools and experiences. So now it's up to you to decide whether something is a tool or whether something is an experience. So the first one certainly was one. It's the third time that Julia showed up at the conference. We had somebody implementing an analysis in Julia, and what they were finding is that they can get to the same speed as the classic analysis. And in some benchmarks, which are relatively simple selections, they even outperform Root. We had Service X, a really interesting service which runs on a remote data center and can give you a subset of the data, so that you're only downloading a really small part of the data on your laptop with the part that you're interested in. We saw a lot about what's going on in the awkward ecosystem. It's, so to say, the Python equivalent of a root tree. It's a bit oversimplifying. But what I really liked about it is to see how the ecosystems now, they start to touch and integrate and talk to each other. Awkward used to be the Python equivalent of what you would do in Root when you analyze the T3. But now you see that it's talking to C++, it's talking to Root, it's talking to Number, it's talking to GPUs, and it's really great to see how those things all start to integrate and really grow. If you are using the Root interpreter and you have ever crashed it, your program, the interpreted program, this is the talk that you have to look into. You can now debug and profile your interpreted code. And finally, we were looking at how we can make the life of analysis people easier by getting the nitty-gritty things like calibrations and systematic uncertainties and deriving an n tuple for further analysis. How we can do this more centrally and get it out away from the shoulders of the analysis people. And then we came to the last session, and here I wanted to just quote something that I find also is very telling for this conference. Thomas said, I heard at this conference, Hot.io, it's an EPM development toolkit, is in use by several communities. And he only noticed, apparently at this conference, and this is exactly what we're coming here. So it's great to hear this. I don't have much insight into what quantum correlation functions are, but they can be extracted with something like almost differential programming. And then we had the final talk by Remco, and here we messed up the scheduling. He was talking in his abstract about a computer algebra system to do partial wave analysis. And what we didn't notice is that this is one of the most transformative things in doing any kind of fitting, because they're using something like Mathematica, SimPy, to write down the thing that you want to fit, and this thing spits out the code in Fortran and C++, Python, whatever you want. And this one should have been totally in the fitting session. And after we closed the session, said thank you to everybody. We're like, wow, did this guy just tell us how to do fits in the future? But then it was already over. Okay, so what I'm taking away from the conference is we will take a huge leap forward in terms of I/O, what size and read speed is concerned. There's two analysis ecosystems. You know, there's Root and there's the Python ecosystem, and they used to coexist since quite a while. But what I'm seeing now at this conference is that they're not only the developers are talking to each other, but the software does so too. And this is really nice to see as a development. They're all doing amazing things. We're trying to take away the complications from the analysis people, and sometimes we're managing. Machine learning is everywhere. Julia entered the stage, but I don't really know yet where we're going. And the N in the chat is certainly audible these days. Thank you.
Thank you so much. We have maybe like time for one short question. Okay. Okay, then perfect. Thank you so much for a very nice explanation. And
No, yes, now, okay. Thanks for coming back from the coffee. I think we restart the highlights session summary and we go with track 7, virtualization and facilities. Verena.
Hello. Okay. Oh, yeah, that's okay. Okay. Thank you so much. So I'm gonna summarize track 7, facilities and virtualization, on behalf of the other track organizers. So as similar to other, we've heard about other tracks. So this track covered several topics. We had 7 sessions. We had 41 presentations in the track and 21 posters. And of course, it's a challenge to summarize everything in a few minutes. So I'm going to try to highlight some of the topics that came up in the discussion. And please take a look at the presentations for more details. We heard about a range of topics, including the new HEP score CPU benchmark for WLCG that has become available, that is better suited for 64-bit architectures, and also is now available for a range of hardware options, and we will be transitioning to. Of course, in this track, a common topic was about virtualization and containers. We heard about features of containers, in particular, Aptainer, formerly known as Singularity, has increased capabilities to offer sort of container installation, satisfy container installation needs that users want, while reducing the risks for sysadmins. We also heard about initiatives for container registry, discoverability, visibility, and traceability that also offer capabilities such as vulnerability scans. And we also heard about a Kubernetes provisioner that is demand driven. And here the use case is the Open Science Pool, which is a virtual cluster that aggregates a large number of different resources. And the idea is that you want to enable, provide resources only based on demand and not, waste them otherwise. So do so efficiently. We had several talks about computing facilities that were really focusing on automation, increased operational intelligence, and improved efficiency. We heard about, for example, a framework that has been implemented for automated server management for the new data center at CERN. And here, this follows servers across the whole life cycle. And you can see that now there's like up to almost like 10,000 nodes. That's hundreds of thousands of cores that are sort of managed in this way. We also heard about mechanisms for automatic remediation, which is great for managing batch worker nodes, and also improved, reduced maintenance needs by, for example, having a mechanism to reduce file system overloads, which is a problem that can come up in clusters that have many users. We also heard about use of AI to improve the operation of facilities, for example, using anomaly detection to identify when there's a power outage or something like that. We also learned about systems to deploy cloud services that are fully integrated in Git and very streamlined and are also available using these new technologies. Okay, we also heard about computing facilities and infrastructure. So several resources are transitioning to new data centers that just have better, cooling capabilities and power. And just another issue is for the future is just having more space to be able to expand. So we heard about the new data center at Brookhaven and also the transition of the INFN CNAF to the Technopolo. And then we also heard about some dedicated solutions that really have specific experiment needs. So for example, the LZ experiment has IT infrastructure, deep underground. And so, we learned about some of the challenges, including, routing dark fibers in the dirty environment of a mine, which maybe is not a concern for all of us. Another topic was critical services and control systems. So of course, some of the concerns for these types of systems are security. So we learned about new security features, for example, incorporating Vault in the CMS web system, but also improved system management. So the experimental control system infrastructure for LHCP uses a virtual machine framework that has shown it's much more capable at disaster recovery. Another very widely discussed topic in our track was the various efforts to improve energy efficiency and reduce the carbon footprint, which, as we also heard in one of the plenaries, are not the same thing. There are some initiatives, some proposals to actually measure the carbon footprint and provide feedback. And in particular, the embedded carbon footprint is becoming more relevant. We also saw an estimate of the environmental impact of a fairly large tier 2 for example, the usage of the power usage per core and per terabyte then can be translated into sort of the carbon footprint, and you can see that that's comparable to having several hundreds of sysadmins flying across the Atlantic. Another interesting proposal was about a data center refurbishment where the heat from the data center is used to heat water that is then used across the campus and is in the future planned to be used even for some of the residence halls, to provide hot water. And this can, provide significant carbon savings. Of course, in this track, we couldn't, we also had several interesting talks about high performance computing and HPC centers and how to really integrate them into our computing. We heard about the use of the Tianhe 2 supercomputer for BESS-3 in China, which is now was able to solve issues such as, data access and other things. We also heard a very nice talk from the, about the integration of the Barcelona Supercomputing Center for CMS, which is now able to provide significant CPU resources above the baseline, tier 1 resources. And they had to overcome limitations, for example, in network connectivity. Oops. Another topic related to HPCs is, of course, the possibility of using heterogeneous architectures. So there was a discussion about integration, the commissioning of GPU resources in HPCs for CMS and sort of where this is going in the future. We also heard about large-scale HPC deployment for scalable cyber infrastructure, where the use case is a certain machine learning workflows, and they've been able to implement this, and they're using Rihanna, so we can accommodate more complex workflows. There is also expanding experience with cloud resources. We heard about several of the opportunities for new ideas and evolution, the complementary resources that are available in some of these facilities. Also, we heard about elastic usage at commercial clouds, which have been used, for example, in Atlas. You can see here, this is an increase in the CPU resources that were scaled up to a point that they were sort of one of the largest providers for a time. We also heard about the access to new architectures, for example, significant numbers of GPUs also on demand. And also on Amazon, the larger numbers of the ARM processors for simulation. We also heard about cloud native solutions for machine learning as a service. So the idea here is to be able to integrate resources that can enable analysts to carry out their machine learning trainings and so on, and then incorporate them back into their analysis workflows. And another interesting talk was about a tier 2 in Atlas that is fully cloud native, and it's part of a bigger cloud system in Canada and provides both CPU and storage. Okay, we talked about analysis facilities, which is a topic du jour at the moment. And I'm not going to try to define that, but we're basically, what we were discussing were sort of approaches to support analysis workflows with integrated data services and computational resources. We heard about the shared facilities in Atlas for the US with federated access. Also about the web-based interfaces of an analysis facility for LSST. So a lot of the interest is to aim at consistent and convenient, having a good user experience. And there was another example for the Signo experiment. We also talked about some of the infrastructure, so improving the data access and reducing the I/O latency, for example, with Xcache, and also improvements to scalability and turnaround time, which can hopefully reduce the time to insight. We also heard about various solutions for how to optimize opportunistic resources. For example, using the high-level trigger farm for Atlas, and how this can now accommodate different workflows also for different lengths of downtimes. Maybe even as short as like between fills. Also, we heard about the implementation of a federated heterogeneous system for compute and storage for nuclear physics needs across Germany that offers container registry and batch overlay system, among other things. And finally, one of the other key topics that we covered was networking. So we heard about the transition to IPv6 to overcome some of the limitations of the number of addresses available for IPv4. And you can see here that, for example, for the fraction of T2 storage that is accessible via IPv6 is really now reaching the majority of tier 2s. And we also learned about some of the technical challenges that had to be overcome to sort of increase the amount of data, the amount of storage accessible by IPv6. One key aspect is monitoring. So we heard about a way to tag data for monitoring, and also this makes it possible to do more detailed network traffic analysis and further optimizations. And these are sort of key aspects towards a vision for the next generation of a network integrated system. So the idea, the vision that we heard from the Global Network Advancement Group is really about the need for global coordination across the major networks in the world, and a vision where we have a flexible dynamic system that balances and makes best use of available resources. We have several ongoing R&D projects. We heard about like regional caches that allows data sharing among users in the same region. And we also heard about ways for more intelligent control and optimizations. For example, the Sense project aims to integrate workflow, connect the workflow and network so that they interact and are able to plan and negotiate resources and offer a quality of service capabilities. And finally, we also heard about an intelligent network controller that is able to detect large data transfers and optimize those so that we can avoid link congestion and other issues like that. So that brings me to my conclusion. So it's been a whirlwind summary. We had a lot of very excellent contributions, and you can find more details in the links to the slides and also in the proceedings. Thank you.
Thanks a lot, Verena. Any burning question? Thanks, Verena. Thanks again. Thanks to all track. So next talk is about Michelle Villanueva, will be about reinterpretation and collaborative tools, outreach and education. So next talk is about Michelle Villanueva, will be about reinterpretation and collaborative tools, outreach and education.
Thank you. Right, so it's for me a pleasure and honor to present on behalf of the other conveners highlights of our track that contains 4 concepts: collaboration, interpretation, outreach, and education. As we were learning during the session, every time that you think in one of these concepts and you design a strategy, you have to take into account the others. So they are closely interconnected as we will follow up. Let me start with the very first highlight, that is the people, our speakers, because thanks to their careful preparation of the presentation, the slides, the nice discussion that came after with the questions, all the session was a success. And especially we want to say thank you because everyone was on time. That made our work as conveners very easy during the event. So thank you very much to all of you. And I have to apologize in advance because, of course, for obvious reasons, we will not be able to cover everything. Okay, this is just some overview of the topics. Let's not list them. We will do that in the next slides. So the link for the inputs there if you want to look into the details for one of the things that we will discuss. But here the global picture is that we as a community, particle nuclear physics, are trying to reach other communities within our academic environment outside of the research centers outside the universities, and the public in general, even far away. Okay, let's start with ourselves, with the software citation. In physics, there was an overview of the software citation and recognition workshop. This was a space in which the experiments, the software projects, and the publishers, the journals, discussed how to handle the citation software and the recognition for the software efforts. This is an ongoing process. That was one of the highlights of the talk. So it's a good idea to keep track of how this evolves. And there is a list of recommendations there. It's not the full list. You can look at the presentation. However, let me highlight that it's important to make clear how to cite in your documentation, and also that the pragmatic discovery of the citation is important. So it's a good idea to consider use APIs. Also, it's available this citation file format that is becoming a common standard, is supported by GitHub, supported also by Zenodo. So if you put this in your repository, you will have this box in which it says clearly how to cite your project. Okay, and moving on. So, Zenodo, happy birthday. We had the opportunity to celebrate the 10th anniversary of this tool that has become quite critical for the community. It's a repository of everything, basically, and Lars gave us a very nice talk about how the trust for this tool was built across all these years. Now they are providing support to more than 300,000 users in 133 countries. You can send a birthday greeting if you are up for, and also we had chocolates to celebrate in the session. That was really nice. Okay, let's switch gears to open data. We had an overview of how the experiments try to implement the access to the data to other communities outside the experiment. It was a nice overview from Atlas, how they managed to make discoverable data sets with a web interface. In the case of CMS, that they carefully check each one of the steps to avoid later having to do some detective effort in finding what is the data set that you want to release. The Entable Wizard in LHCb, it's a very nice interface for the people in the community to just select what you want to use for the analysis. And Micromoon provide, in addition to the data, also a set of Jupyter notebooks for using the information that is available publicly. It's very interesting. You can take a look at the slides. However, something that came in the session is that the common challenge for everyone is how to publish data in formats other than root, such as you can, in principle, enable, for example, HTML5 or any other kind of format that may be convenient for outreach or for any purpose in general. Preservation, another important topic. Let me start with the LHCb. They show us how they make the track, the first steps in the analysis, the initial workflow, and also the environment that must be preserved. Here, the keyword is metadata. Data sets, everything in general must be discoverable. You should be able to search what you need. Also, in another talk, Babar shared with us their experience making the preservation of all the information that they have in their old systems and migrating to the new one. So you can see this is a crystal ball of what could be the future for some of our experiments. In general, what Marcus was saying is that data analysis preservation can be done, but planning early for it can help a lot. So in other words, embrace using virtual environments such as you can make portable your documentation, your repositories, and so on. And also it's a good idea to use open source. And finally, we spot some UFOs in the session because we were talking about universal fine rules output models. And this was very interesting because it's an object that is not directly related to the analysis. However, it's an object that is used for the phenomenology, for the models, and there is some effort in order to make this, to make track of this with the FAIR principles. How? You guessed right, using metadata, using a repository as Zenodo. So in principle, anyone can take any of these objects and reproduce the work that is done in the phenomenology and the Monte Carlo models in general. Collaborative infrastructure was already mentioned. Some of these initiatives, Punch, the INFM Cloud, and this is also the national initiative in Czech Republic. I will not go into the details. It's a lot that they cover. It's a really nice piece of work. However, let me say that what we identify is that there are similar solutions, different countries, different funding agencies, but similar solutions in the table. So, and a space like chat provides precisely the environment in which they can discuss, they can collaborate, and maybe we can find solutions in common between these different, let's say, ecosystems for analysis. Also, we got a nice update on the Science Box. Now they provide a self-contained and easy-to-use package that provide the capability in principle to use the de facto tools for collaboration outside CERN. And one more interesting approach is the Science Mesh that in principle aims to provide the protocols to communicate all these different communities that in principle are isolated in their own federated resources, such as you can communicate between them. And that's a very interesting initiative to extend the capabilities of the analysis on the cloud. And let me continue with this because these initiatives will usually come with training. So for example, in the left side, you can see the initiative of the ML INFN lecture program that provides precisely data from the different experiments that they are giving support. There are very nice tutorials in which the students can in principle follow up and perform analysis with the data sets that are available there. There is also the initiative to do training for FPEAs. However, FPEAs are expensive to provide to the students. So what they did as a solution is to provide the environment in the cloud. So that is the way that you can simply deploy as many virtual FPEAs as needed. So you can enable this training with the community. That's super interesting. And finally, the initiative of the AI for EAC, that is a hackathon in which they provide a data set and they challenge the community. Okay, can you identify particles, use your tools, give prizes? It's a very nice initiative. Take a look at the slides. Let me continue with the training because in our experiment we also do training. So there are several initiatives and we have a nice overview by Alison about how the experiments follow up the training inside the collaborations. So you can see we have a wide range of options from going fully virtual, like for example, right now, Bethel is using an online group or PIC online tutorials. Dune with a dedicated talk, they explain that they use a carpentry style synchronous format, in which they try to provide tools for the people that is joining. Started Kit in HCV and Atlas with the software tutorials, and CMS seems that it's going more in person events with the data analysis schools. We also say that this evolves because with the pandemic, everyone went virtual. And now that we are in a post-pandemic world, it seems that everything is moving slowly towards the right side. But you can ask, okay, is this really training enough? And apparently it's not enough. So why not leave everything to the experiments? Well, because we can cover more if we do this together. But that's the initiative that the HSF and IDSCAP is putting on the table. There is a full platform of weekly meetings, monthly hackathons, channels of communication, community pages, so to develop a full training program in which on top of that you can make your specialized training for each one of your experiments. So again, we can build more together and we don't have to reinvent the wheel every time that we do some training. So take a look at this and I will invite you to contribute to this effort. I'm running out of time, so I will go quickly. For the connection between academia and industry, this is really important because we need to understand what we can offer to the industry and vice versa, and at the same time what are the needs of the industry solutions that we can provide to them. And this is an example of the Smart Head initiative, in which they list a set of projects that were successful with companies, big companies in some cases, in collaboration with the universities and the research centers. It's a really interesting approach. And at the same time, there is also the approach from Germany of the EROM, at which they don't have projects yet. However, they are already raising these questions on how to do sustainable computing and how AI is used in industry and how we can contribute or collaborate together to solve the problems. At the end of the day, it's two faces of the same problem. We have to analyze a large amount of data very quick. And just a comment as conveners of the track is that it would be very nice to see more of this for the next chapter. Outreach, of course, I don't have to convince you, is very important. We have the IP PGO initiative, that is an international well-established organization, where we got the updates about the new members, the activities done the last year and the current year. A reminder that this is not about, this is not high technology, it's just people putting the effort in order to enable the outreach at the international level. And at the same time, there are some local initiatives that are very interesting, like, for example, the remote tree that talks about remote sensing by remote schools in remote environments. So places in which usually the students don't have the resources to go to the research centers to get some feedback or feeling of what is doing science. So they provide the tools to send that experience to remote places in the UK. And also the initiative from Quartnet and Irish Head that takes trains teachers at different levels to provide the tools such as they can talk about the science in general with the students and the software. Virtual visits, again, time's up, so I will just mention that there are two very nice initiatives. One is the virtual visit with Dune, like a video game, so take a look, there is a very nice video, the link, and also the virtual tools by Atlas that enable that some students say, oh, in 6 more years, I could be doing that. This is all about the work. So this is the last slide. I hope I have convinced you that we have a close interconnection between these different concepts. And every time that we invest in one of it, we are investing in the future. It is important. We are accelerating the first research with the collaboration, and at the same time, we are investing in the next generation of physicists. So in behalf of the conveners of the track, let me say thank you.
Thank you, Michelle, for the very nice overview of this very important topic. Any question? Doesn't seem so. Well, so thank you again. Thank you all the track conveners. And we continue with track 9. And Sofia Vallecorsa is going to give the overview. Yes, it's a guy. It's one.
Okay, we are approaching the end. I hope you still have some buffer for attention. This was a very interesting track. Track 9, artificial intelligence and machine learning, and you saw already how much you heard about, actually, how much you heard about machine learning until now. So this is really, really good news. The topics of our tracks were scattered across many different applications. And what you see there is actually the word cloud that we made by looking at just the titles of the presentations. And it really shows that there is a very broad spectrum of applications now, going from reconstruction, physics, online processing, general methods, and so on and so forth. And we also had, as Marilena mentioned before, a shared track that is dedicated to fast simulation. This is really one of the hot topics. As all my other colleagues here, I want to already apologize for all of those that will not, those excellent talks that will not be explicitly mentioned. It was very difficult to choose. I had to make fun. We did have to make fun choices. So I know I'm typically late. I'm actually the only person whose name is capital on the agenda. So I might decide that I will not stick to time. But just in case I'm cut. I want to give you the highlights right away, and I will go through all of them, through the talk. But at least at this time already what I think are the most interesting and most important parts that came out of this track. So first of all, the fact that machine learning shouldn't be considered a black box. In fact, the fact that machine learning is not a black box anymore. This is something that has always been mentioned against this kind of tools, and it's something that is not true. And I will show you how many examples we actually had about this. The other thing that came out, and it was really difficult to keep track of all the applications that are looking into either point cloud or graph representation of the data or graph approaches to processing, is the fact that graph neural networks are in fact ubiquitous across all applications. And you will see it coming through the different slides in different experiments and different levels of data processing. Another interesting thing is that we've seen a lot of new architectures from a point of view of model topology. And it's very nice the fact that we are not just simply transitioning towards larger and larger and larger models, but we make smart use of the topology of those networks. We try to optimize that to the problem, and hence we combine them in hybrid setups. So this is very important. And I wanted to stress the important part of that sentence, because in many cases, what we're doing is to understand that we can use tools that are used in different fields, industry or other sciences, and then apply them to our problems. There was a lot of discussion about new learning patterns, continuous learning, active learning, new ideas for improving the overall training process across multiple applications, the definition of different losses. We also had a nice new losses that was presented to us, inspired by work at Twitter. I'll tell you about this. And of course, for simulation. Simulation is clearly moving beyond GANs. This is also good news. I love GANs. We started in early 2017. First presentations of GANs were color GANs and my GANs at Hackathon 2017. So don't get me wrong, those are great, great architectures, but there is a lot of work that is ongoing in exploring alternatives, and this is already presented also by Marilena. But of course, GANs are in production and others, so we shouldn't forget that. Okay, let me go now through what I just briefly showed to you. Why machine learning shouldn't be considered a black box anymore? Well, first of all, we are starting to understand how to take into account uncertainties. There was a nice example about this, about uncertainty modeling and how this should be used to present results in a way that does not generate problems. When the models are used, this goes beyond science, of course. I mean, our direct applications in physics is a general problem, and it's something that the whole machine learning community is looking into. There was also a nice presentation that was actually dedicated to introducing a new methodology for improving limit setting. But what I wanted to stress, and the reason why I mentioned this in this case, it was a nice example of analysis reinterpretation. So the idea of going back through frameworks that are designed to help reuse and reanalyze data and improve on the limits of what was done before. Interpretability, of course, is another big issue, not only related to, again, uncertainties modeling, but also as a tool to improve the performance of those models. So if we understand what actually happens, the way those models learn, how the information propagates through the network's topologies, and how it connects or it shapes the internal presentation that those models learn, then we can use this information also to get better performance. And connected to this, although much broader, is the discussion about fairness. Fair as findability, accessibility, interoperability, I have to read, sorry, reuse of all those digital assets. Again, this is something that goes beyond machine learning, but it's particularly important when developing a machine learning algorithm, because there are different steps that are different components that need to be taken, need to be available, properly documented and shared, so that the overall pipeline actually works. And this can lead to very nice examples and cross-fertilization and across different domain. You see an example there of point cloud model developed in app that is used in a completely different environment. Another example, new methodologies for machine learning and beyond machine learning. The idea of differential programming is, well, maybe falls more in the category of renewed, completely new. But we have quite some interest on this, mostly targeted to detector optimization. So the idea of formulating the problem of designing a detector as a multi-targeted, multi-objective, very complex, multi-objective optimization problems for which we need to actually develop the tools. So there was a nice discussion about new methods for automatic differentiation in the scope of discrete stochastic problems, which is absolutely not an easy task. but also machine learning based optimization of detectors configuration. So in particular, I can't avoid mentioning the EPIC detector that is really the first example of a large scale experimental design using AI. If we go back to what I was talking about concerning complex or smarter architectures, you will start seeing now examples of models that actually merge and mix and match different kind of networks. And this can become a very, very powerful methodology to use. You see here an example for clustering algorithm that combines current neural networks to convolutions, and each one of the parts of the components in the networks is actually focusing on a specific aspect of the problem. So this typically works very well. And another example instead is more of a pipeline that's designed for designing primary vertex, for solving the problem of primary vertex identification. And this was a nice talk that was actually a shared talk between Atlas and LHC. Tracking, of course, is a big customer for machine learning algorithms and graphs in particular. What I wanted to stress in this case is the fact that tracking itself can be formulated as a multi-step problem. So if there are actually many different ways of approaching this, either trying to build end-to-end pipelines that solve the overall problem as a whole, or trying to solve specific tasks within the tracking itself. And so there were nice discussions that came out about introducing object condensation, which typically can speed up clustering, and it's a technique that uses different fields, or combining together models that are again trained for specific steps and then matched. And this was an example that we got from the classical experiment at Jefferson Lab. Along the lines of reconstruction, I would say we had a lot of contributions from the Dune experiments, so collected a few of them here. And again, you can see what I mentioned before, again, the importance of graph neural networks, the importance of coherent set of tools that you can integrate. And in particular, what you start to see here is the idea of integrating machine learning tools within different software and algorithms. So not necessarily really trying to replace entire parts of your software, of the software stack, but really just introducing and optimizing the transition, the pre and post processing steps that are needed in order to properly use machine learning within other workflows. And we have examples of this, as I said, from Dune within the Pandora framework in particular, and for other tasks. Anomaly detection. This is an interesting slide. Typically, when we talk about anomaly detection, we talk about applications for physics and analysis, triggers. I think it's important, especially in a community which really leverages large infrastructure, both at the level of computing, but more in general, engineering infrastructure for detectors or accelerators. It is important to realize that there's actually a lot of work that's going on in this field. And so those are two examples of using anomaly detection for hardware studies, and in particular, anything that has to do with fault detection, preventing maintenance. Those are topics that are very, very hot, I would say, in the broader industry community. So you see here two examples, one for high voltage controllers at the SNS LINAC accelerator, and another one for RF cavities of free electron lasers as well. Since I mentioned online applications before, online applications has always been very interested. Online applications, yes, I've always been very interested in machine learning, looking into machine learning, because once you train the machine learning models, that's typically faster. Now we're starting to get to the point in which latency requirements also start to be tight, also for machine learning algorithms, and this is triggering a lot of research, both at the level of speeding up machine learning inference, at the level of deploying it on dedicated hardware, ASICs or FPGAs, and at the level of looking into alternative paradigms actually that can optimize machine learning or provide faster, smaller, more optimized models. So continual learning is a particularly interesting paradigm for learning. This is really dedicated to changing and dynamic environments. Cases in which you don't want to retrain your model every time configurations of your environment change. And this has a certain set of also requirements and at the level of the computing infrastructure that's needed in order to setting it up. And this was this nice example from the CMS level to trigger, in particular the vertex time. Yes, okay. I wanted to mention symbolic regression, but this is something that, because this is a completely different approach that's also very, very promising. And well, I will skip fast simulation because you heard about this already. That the general discussion about fast simulation is really the fact that we are looking into models that we did not use before. And some of those have been showing great performances outside of physics. Many examples, you will be able to scroll through the slides. Maybe I could just end with a slide on the tools, because we couldn't really do much about machine learning without properly acknowledging the setup of frameworks and tools that the community then can use in much broader set of applications. And so you can see some examples in these slides. Thank you.
Thank you very much. I guess it was challenging to cover all the topics of the track. Any question?
Hi. I think, it's just start from an observation. There is a lot done in offline software, online software, hardware anomaly detection. I didn't see a lot in what is in the middle. So machine learning applied to optimize the way we run services, computing operations, and things like this. So I think my question for you as a track convener is, did I miss something? Or, this is a summary, maybe there was something else. But if I'm right, the next question is for you as an expert, what do you think we are doing wrong? Because other sciences or disciplines, they are pretty successful in this.
Okay, I prefer to, so indeed there weren't that many talks, there weren't any talk dedicated to optimizing services. Now, I completely see your point and I completely agree with what you're saying. I would like to reformulate the question as not what we are doing wrong. I would say, what are we not doing yet? I think there are a lot of opportunities to actually use those tools to improve services. This is not something that has to go necessarily from one day to the next in production, as we know very well. But this is already happening in different environments. So you can do optimization of your resources. There have been examples in other tracks about deployment optimization for different workloads. I think there are a lot of opportunities in general.
Any other burning question? Not, well, thanks again, Sophia, and thanks all the track 9 conveners. And last overview of the parallel session tracks is Stephen Tim, who's going to present the highlights from track X that includes quantum computing, exascale science, and heterogeneous hardware. So let me go. Oops.
In my computer.
Okay. Oops.
In my computer.
Okay. Okay.
All right, thank you.
Thank you.
Yes, we had 3 tracks, 10, 11, and 12 put into track X. My co-convener was Rural IH. I did not see his name right. And with exascale and heterogeneous computing and quantum computing, we're doing all these same things that are done in all these other 9 tracks, but we're doing it on bigger hardware in some cases or different hardware in other cases. This plot featured in probably at least 10 of the 41 talks that we saw, and here the Agile LHC is coming. where do we get all the computing power from? So this is a driver for all of HEP. In the Exascale, we had 3 presentations from IFN on their new infrastructure that are coming. I think that's significant, very expanded network from what they have previously. The guard network getting extended to places it has not been before, and increasing its speed, some new HPC centers, new big data centers, large increment of funding. Dig into things to find the numbers there. They are moving to technical. There was quite a bit about that. Just one talk on INFN's companies that are moving into technical, another on the Exascale supercomputer, which is there, which they believe was top 4 in the number 4 in the top 500 now. So this is a very big investment with many millions of euros involved. Also from INFN was network interconnects. This is actually something big in Exascale that to go to the next level, you need better interconnects than what you've got now. The Red Sea architecture and another one that was called EJFAT from Jefferson Lab. Both are dealing with 2 problems. One of interconnects inside supercomputers and the other of interconnects from the edge services straight from the experimental hall to the HPC center in a seamless way of data flow. I should have said I'm picking one slide from each of the presentations that were given in the tracks. All the good stuff is there, all the errors are mine. So you need an Exascale parallel I/O, HDF5, or was mentioned a couple of times in different talks. Got very good parallel writing performance. And you need compilers that can drive parallel things. This is actually a recurring theme all the way through not only Exascale but Heterogeneous. This is from between one of BNL of how are you going to extend Lattice 2CD onto new and wonderful hardwares. The other theme that went throughout this thing is not just NVIDIA GPUs anymore that we have to deal with. It's also Intel GPUs, and it's also AMD GPUs. There are 3 Exascale or leadership class facilities being deployed in the United States, and each one of them has one of those. And Lattice 2CD is typically application that's run on supercomputers in the past, and they're well on their way to getting there on this. As we move to Heterogeneous, Charles Leggett of the HepCCE project let us off, and this matrix was shown at least 5 different talks. It really should have been plenary. We pushed it for plenary, but he got through it in 15 minutes instead of the 30 he wanted. But you see across the top the various tools that are used now, including being a period, Cocos, Sickle, HIP, OpenMP, Alpaca, and SPDFAR, and then the various hardware types on the rows. And they explained that when HepCCE started 3 or 4 years ago, this was almost all red, and now they have it almost all green to the extent that it can be. And as part of HepCCE, they actually ported several key things, Pentatrack, CMS, Wirecell from Liquid Argon and stuff, Pascal Sim from Alice, P2R, which is a generic tracking program. And there were 5 other talks on that, which will be given some pieces. My apologies that I picked PDFs out of things, and not everybody uses the same aspect ratio. So what are we using heterogeneous stuff for? Well, the low-hanging fruits, well, these are low-hanging fruit, but they're very substantial fruit. Optical ray tracing. In particular, there were 2 talks on this one, written by Simon Bliss, but given by Carl Lin, on taking NVIDIA ray tracing optics, which is on some of their cards, and then making the OPT ICK software package to use that. So first one covered ray tracing for Juno. The second one covered it for Liquid Argon. Liquid Argon HPC behind Wenzel. This is the CAS simulation here. Let's see. What's the next thing? This is Corsica. Again, the cosmic ray shower, lots of EM, lots of photons, easily handoffable to GPUs. Then Accelerators, which is a more structured effort, currently basically acting as plug into JN4 to do EM calculations, basically hand up all the electromagnetic Accelerators. This is Oscar funded part of FCCE also. Okay, next thing, well, thinking for MedGraph, which several LHC experiments run. You have many matrix elements to count. They're perfectly suited for high parallelization because you can do many calculations in parallel. The code has very few branches, which is important for heterogeneous things. So they've got quite a bit of gain running this parallel on CPUs. With also the next thing of as you go to next to leading order, appropriate tool is reweighing. Reweighting things. You have various diagrams that show up in the next leading order as well. You just need to do reweights. You don't have to actually simulate the whole event again. My apologies, the full screen on my Mac, these all showed up in the right size. I'm not quite sure what's happening in Windows here. Next, we're looking for random numbers. Most of my parallel is spending much time throwing random numbers. Turns out they're not a very good GPU random number calculator yet. So this work ported the mix from JN4 into native GPU code. It's achieved very good speed up and good reliability also. High level trigger. Now we're moving towards how are they using them in production. This CMS slide showed up in at least 3 different talks, a factor of 2, well, not quite a factor of 2, but from 690 to 397 milliseconds. Is it milliseconds? Yes, milliseconds of calculation time. CMS also showed a talk about workflow management for GPUs. It's this one here. How do you get GPU workflows out to the various places on the Open Science Grid and IHPC where you've got GPUs? They're doing with HT counter matching. The next talk was from LHCb, actually 2 talks from LHCb. One about their online trigger being very GPU heavy now, and also thinking how do you extend direct to talk to various kinds of supercomputers, and they dealt with all topologies. Those which have good network connectivity from workers, those that have no network connectivity from workers, those that have no network connectivity at all, and all possible combinations, all permutations of that. Let's see. Then Exascale for Alice. Taking Exascale from Alice, porting that to GPUs. LHCb Rico, machine learning within LHCb Rico on GPUs, both training and running. This is the architecture of, we're now getting really heterogeneous. And this, by this, we're putting either FPGAs or MCPUs inside storage, on storage CPU. So the IHAP has a modified version of EOS, which is using storage CPUs as a thing so you can compress or you can sort a file as it's being pulled off of the drive, basically. One slide on ARM GPUs for IceCube, which this is their got very good performance on IceCube. The Corsica code, although it did take some work to port Corsica to ARM, they did it. Now moving toward more generalized services, they made this is INFN, made an extension to Kubernetes kubeflow to serve FPGA clusters in their so-called bond machine. This is a very interesting talk, as you can look it up. The Sonic project, which has worked with CMS. This is now not in online, this is the inference on the analysis end. Now, pretty good. GPU, your inference as a service with a Triton server. This has been used for CMS, also been used for Dune. Pixel clustering with FPGA for LHCP. Neural networks in general readout systems is a very generalized platform from the AFN. A very good talk on quantum. Now we come to classifying the various kinds of quantum devices that there are. Read Maha France's talk. If you read nothing else than quantum thing, this was a very good introductory summary. We just happened to put it first. It was good that we did. Most of the ones that were talked about in the quantum session were transmon type of quantum devices. But all these people were doing something with real quantum devices. That's how they got neural. It's not just, none of them just theoretical. Noisy simulation from trees. Quantum angle generators, vision transformers, quantum vision transformers, quantum decision trees, quantum support vector machines. This was interesting because you used not only one that was qubit based, but one that was also continuous variable based, such as a harmonic oscillator, quantum machine, Higgs classification, another quantum support vector machine. Continuum suppression. In there was one quantum annealing. So we basically cover, this is basically show you can do real physics with quantum devices as they exist right now. And I think we should probably have a full quantum track in the next chap. The Kibo framework, basically rudimentary operating system for quantum devices, and then batch systems, Krakow hooking up to spaghetti. And that is it. I think all my presenters that presented, they all did very well. And if I missed your work or if I mischaracterized it, come see me afterwards and I'll get you lunch.
Thank you, Steve. Thank you. Any question for Steve? I don't see any. So let's thank Steve and all the TrackX convener again. Let's also thank again all the track conveners for the work they've been doing. And with this, I'll let the floor to Amber. Thank you. Any question for Steve? I don't see any. So let's thank Steve and all the TrackX convener again. Let's also thank again all the track conveners for the work they've been doing. And with this, I'll let the floor to Amber for the closing.
It is my pleasure to close this this conference and to thank all of you. Okay, there we go. So there will be a survey that'll be sent out to all of the attendees in email. So please watch for that and fill it out. There are a number of reports that will be based on this, and so it really is important to have good uptake on that survey. So please do that. We'll also be sending out information. I'm sorry, I couldn't. There will be information on the proceedings, and that will be sent out soon. It'll be a similar process to previous years. The nominal 8 to 12 pages, including the figures, and there are templates available off of the CHEP 23 Indico page under proceedings. Be a good friend to yourself and to your future self and write your proceedings promptly, please. The next CHEP will be on you before you know it, and so you'll want to have this one closed out so that you can move on to the next one. So speaking of the next CHEP, CHEP 24, we had many great bids from locations throughout Europe. That made the process difficult, tough to choose, but we can all rest easy that it was not possible to make a bad decision. So we look forward to joining you at CHEP 2024 in Krakow, Poland. So I believe there's a movie that they weren't able to join us, but they sent a movie. So. So now I will move on to the thank yous. So many of you know that when I have an out of office message, I often put a quote in there. And so I found a really appropriate one for this. I want to echo Liz. It's so great to be back. It's so great to see all of you in person. And so it's true when you meet your old friends, and many of you I've worked with for more than 30 years, it does bring you back to fond memories. And you do find yourself with a joy that you have that has no comparison. So thank you so much for coming. Thank you so much for all of the excellent work that you've done that contributed to this amazing program that we had, both in the plenaries and in the parallel sessions. It really was a wonderful CHEP from a programmatic point of view. And for that, the local organizers cannot take credit. That is all on you. So thank you so much for that. Now I have to move on to some other thank yous for people who did a lot of work behind the scenes. So first off, I want to thank Graham Hayes, who has been my partner in many escapades. And so all of the thanks are from the both of us. The Marriott has been with us this whole journey. So we put in our bid, we started the work on that in May of 2019. So for us, this has really been about a 4-year long voyage. Visit Norfolk and the Marriott have been with us that entire time. And at that, I want to also give a thanks, a very strong thanks to our AV crew, right? Because they've really made things run smoothly. And that kind of continuity that you see, that also just gives a great impression for the conference. So thanks. So we started off with the WLCG workshop. That went really well. That reduced my stress level when that went well. We have our special guest panelists for the Scientist Walks in the Bar, who were also track conveners. So thank you guys for that. And now I want to turn my attention to Anita and the people from staff services who have worked very hard and to make all sorts of things run smoothly. And so thank you for that. And thank you for choosing wonderful food and making sure that the catering was, I can't remember if Attila or somebody commented, oh, I didn't think you'd have enough food, but we did. So thank you. Thanks to Anita for that. I don't see Logan. Oh, here she is. So it took an enormous number of volunteers and keeping a lot of different balls in the air. And Logan joined us and JLab, I don't know, about a year and a half ago. And so she stepped right in and started doing all of that work to keep everybody going and working hard and making their deadlines. And that was something else that really contributed to how smoothly everything ran. So I also want to thank all of the volunteers again. I want a special call out to Paul Letta and Dave Abbott. So they braved the tunnel traffic multiple times a day to bring all of the Jefferson Lab folks here and many of the volunteers here, proving once again that Jefferson Lab staff have no fear. And finally, I want to thank Brad. So Brad Swatsky joined us in CST. He came over from physics. I can't remember when. It feels like forever, but it really wasn't that long ago. And we just sort of had to toss him into the deep end. And we knew we were doing that to him and we felt awful about it. But what we didn't know was that we were throwing a triathlete into the deep end. Brad has done just an amazing amount of work and kept everything going smoothly. The gratitude that Graham and I have for all of the work that Brad done knows no bounds. So thank you, Brad. So once again, thanks to our sponsors. That's again responsible for good food. And I want to wish you all safe travels.